This video is going to walk us through a key framework for environmental science called the Planetary Boundaries. The Planetary Boundaries was developed by a team of researchers in the early 2000s, particularly out of an organization called the Resilience Alliance in Sweden. And what these researchers did is they quantified human impacts on the planet according to a series of planetary boundaries, or what the different impacts are, and what the threshold is for human existence on the planet, and how that has changed over time. And this is such an important concept. There's actually movies about it. Netflix has a nice movie about it. There's TED Talks about it. And I use it as the basis of my Intro to Environmental Science class. So the planetary boundaries use this concept of a safe operating space, which is the boundary that we do not want to surpass as humans in order to protect human civilization. And they base this boundary on something that we call the Holocene. Now, the Holocene is a geological epoch that has began about 10 to 11,000 years ago. And this geological epoch is rather interesting in the course of human history. Why? Because it's the time period in which all of human civilization as we know it seems to have developed. And we think that part of the reason this might have happened is because of the particularly stable conditions of the Holocene, and particularly the stable climate that we have had during the Holocene. And during this time, we had, for example, the invention of human agriculture. And human agriculture is what we believe was really allowed us to develop the civilizations as we have them today. So scientists use this knowledge to say, hey, these are conditions we probably don't want to mess with too much, because if we mess with them too much, it might inhibit human ability to survive and thrive on this planet. So as you can see in this framework, the inside of the boundary is that green safe operating space where they say each of these factors, if they were in that space, would be like Holocene-like conditions. Now, one aspect of the boundaries that they talk about a bit in their papers, and this is a paper that comes from 2015, so the first figure was from 2009, and now in 2015 they said, we're starting to understand that there's this zone of uncertainty that once you pass the boundary, we don't know at what point each of these factors might become a bit catastrophic. And so they show this idea of a threshold or a tipping point. And what you can see here is that it's going along, and when you hit this threshold, things start to collapse rather quickly. And that they're not fully sure where it happens, which is again why they say, let's use something we call a precautionary principle. Let's stay in the green space, because once we're out of that green space, things could get bad in a place where we're not really sure where that's going to happen. And you could tip into a new state, as you're seeing here. And what we do know is that sometimes at local levels, we've already surpassed these thresholds. So you're seeing over here that at local levels, that we might have surpassed some of those thresholds where we've moved into a bad state. But at the global level, little by little, things are becoming more cumulatively impactful. So that's important when you consider how each of these boundaries might have been transgressed at a certain level, even if at a planetary scale, we might still be okay. So back in 2015, they said, hey, freshwater use at a planetary scale, we seem to be okay. We seem to be within the boundary. But that didn't mean that people weren't in red areas where they were suffering because they didn't have access to fresh water. So it's always important to consider that these boundaries might be experienced very differently at a local scale compared to a planetary scale. So this is the 2015 update of the original diagram that you saw of the planetary boundaries. In the 2015 update, what they did is they really concretized what the boundaries that are, which you can see here in bold, which is our biosphere integrity, land system change, freshwater use, biochemical flows, ocean acidification, atmospheric aerosol loading, stratospheric ozone depletion, novel entities, and sadly, crossed off the top would be our climate change. And what they did is they updated it with new data that I'm going to show you in a minute, and they said which ones have been passed at that point. The most recent planetary boundaries comes from our 2023 paper. and by a similar team of authors. It's quite an extensive list of authors. I haven't actually gone through them to see if every single one's the same, but I would highly doubt it. I'm sure it's been updated over time. But the core authors have been on all these papers. And what they said now is, okay, here's our most updated model. We have new data that allows us to, for example, break down things like climate change into carbon dioxide concentration and radiative forcing and measure those differently. We have new understanding of what our freshwater change is, and then we have updated data for all of the boundaries altogether. And as you can see here, there's no longer anything where they feel like, we're not really sure how to measure that. So what these different frameworks are showing you is a really nice progression of scientific evidence that's been worked on for 20 years, or over 20 years perhaps. Okay, so I'm going to summarize here some key changes that we see across these boundaries that really just help you to understand the changes over time in the science and in the data that they've collected. But I'm only going to go through a couple of the boundaries, so you'd have to go to the original papers and look up some of those authors in order to be able to find, to do this for yourself. So one key boundary that we've talked about is climate change. Okay, in our climate change boundary, they have said they're going to measure by carbon dioxide and by radiative forcing. So I'm just going to do RF for our radiative forcing there. Now there are other aspects of climate change, if you've seen some of my videos, that are impactful that they could be measuring. But these are some really good proxies to be able to understand climate change. And so with carbon dioxide, they did research and they said Holocene-like conditions for carbon dioxide were 350 parts per million of carbon dioxide molecules in the atmosphere. Okay, so if we want to stay in Holocene-like conditions, we should try to keep carbon dioxide in the atmosphere at that level. Well, in 2009, we were at an average annual 387 parts per million. That moved up. That moved up to 398.5 in 2015, and in 2023 that moved to 417 parts per million. So you can see that's continually increased. Our radiative forcing, measured in watts per meter squared, has also been continually increasing over this time period, and so that's really a way of looking quite clearly. We were already past the boundary, and we've moved further and further and further past the boundary. Let's look also at our biochemical flows. Okay, these are really key for our agriculture. We use nitrogen and phosphorus to grow plants. Oops, phosphorus is a P, to grow plants. And these have also been increasing throughout this time. So we measure these in teragrams per year, and we believe that the boundary should be somewhere around 62. And yet you can see continual increases in nitrogen fixation for human use, or amount of nitrogen being used, particularly in agriculture on the planet. And then here we can see also in terms of phosphorus lost to oceans. Without phosphorus, it would be very difficult to be able to continue with agriculture. And in fact, I often tell students that running out of phosphorus is a key concern of scientists that you don't hear as much about, but it is very much real. And you can see that our phosphorus loss has continued to increase over time. So you could go ahead and pull up these papers and chart all of this out for yourself and see, okay, our planetary boundaries, they've been trying to measure these with really rigorous science over the years, and we've continued to sort of continually pass those boundaries.